started by noticing what's on Piazza. Please ask questions. Don't leave it till the last moment. It's not meant to be difficult, but it's also not. It's meant to be one where you try it and then you get puzzled and you walk away and you say, "Aha! Okay, it's much simpler than I thought." So it's not designed to be left to the last moment. Does anyone have any questions about anything before we start? Okay. So what we've been looking at is these so-called single-stage decision networks that are directed acyclic graphs with three sorts of nodes. There are decision nodes, which we draw with rectangles. There are random nodes, which we draw with an ellipse. And there's a utility node, which we draw as a diamond. Each decision and random variable has a range, which is a set of values it can take. The utility does not have a range associated with it. There's only one utility node, and in what we've seen so far, with all of the decision nodes come before all the random nodes, although that's not going to be true later today. And for each random variable, there's a factor representing the conditional probability of the random variable given its parents. Okay, so it's just the same as in the Bayes net. There's a probability for each random variable given its parents. And there's one factor for the utility node that's a factor of the parents of the utility node. And there are no factors initially associated with the decision nodes. So that's where we got to last time. Are there any questions about that? Because we'll play with that and we'll work out how to optimize it. Before we do that, let's do questions. Let's do some. The background for this is, here's a nice decision. Here's a difficult decision that people make. There are a whole lot of schools that are falling down and likely to fall down in an earthquake, and people have to make decisions based on uncertainty because they don't know how they're doing. So people build probabilistic models for earthquakes. People build probabilistic models for buildings falling down. And people then use these models to make decisions about how much money to spend on earthquakes. So here's the question. This is actually a question about the meaning of utility. And we're assuming essentially there are only three choices. You either do nothing or you can spend $1 million, right, to fix up a building. So I want to know so the worst outcome is the building falls down and everyone dies with it has a utility of 0. The best outcome is you don't spend any money and you have no injuries. And I want to spend $1 million on earthquake proofing, and it has a utility of 80. And I want to know what that utility of 80 means. So we had this definition. Okay, so does it mean that if you spend $1 million, only 20% of the students would die? You'd prefer to spend $1 million if and only if there's greater than 20% probability of the worst outcome. C, you'd be prepared to spend $5 million to guarantee to save all the children. Or D, you're prepared to spend $1 million to save 80% of the students. So I want to know what this means. So this utility has a specific meaning. Okay, any question? Yeah. Okay, anyone still need more time? Okay, 3, 2, 1. Right. So B is the right answer. It's all about taking lotteries. It's all about taking chances about how likely you think an earthquake that's going to bring the building down is. And as that probability goes down, then we expect it to be, you're less willing to spend money, and as the probability goes up, you're more willing to spend money. It's all to do with the probability. It's not to do with percentage of students or anything else. It's all to do with taking chances about lotteries of things. And this is something that people actually build probabilistic models using utility to do these things like earthquakes. Some people object on moral grounds. But usually what happens is that if you don't do this, then you undervalue the value of kids. So you undervalue human life if you don't do this. People build this you can model people who make decisions not based on utility theory, and they tend to undervalue human life compared to people who make decisions based on utility theory. Okay, yes?
What's the difference between
A and D, one is about one is about, oh, A and D. Yeah. There's a whole, yeah. I put that up there because there's a whole lot of experiments by psychologists Kahneman and Tversky who claim that people have completely different viewpoints. If you state the same thing in two different ways, people have very strong preferences for what it means. But I just wanted another example for that wasn't a lottery. Yeah, they're meant to be the same. Any other questions? All right. A simpler question. Oh, well. This decision network. The story here is I've got to give a gift to someone and I've got to work out whether I give a gift to them. Whether they're happy depends on the weather and what gift I give them. They don't get to choose the weather, and the utility depends on their weather and whether they're happy or not. Okay, so I just got to choose the gift. So I want to know which probabilities need to be specified. Has nothing to do with the story, but all right, does anyone need more time? Anyone need more time? Okay, 3, 2, 1. Oh, that's exciting. Oh. All right, there's no probability for utility. For every random variable, there's a probability the variable is given its parents. So there's the probability of weather, right? And there's a probability of happy given its parents. Given its parents, which in here are gift and weather. There's no probability of utility. Right? There's no probability distribution of utility. Utility is just a function that's going to specify how weather and happy combine to give me a utility. There's no probability of gift. Gift is not something I get to choose the value for. It's not something that has a probability association. Think about nature gets to choose these other things with probability, but I get to choose gift. So there's no gift. Okay, it turns out the answer here is D. There's no probability of utility. There's no probability of utility. There's just a utility function of weather and happy. Okay, any questions about that? All right, any questions? Okay. I just have a quick question about utility. Is essentially utility, when you think about it, the expected outcome? It gives in the last one, it gives the value, for each combination of weather and happy, it gives you the value of how, the utility of it, where it's good. It's just a function of weather and happy in here. All right, we're at this one. This decision network requires how many factors to be specified initially? At least it's easy to read this one. So. All right, how many are going? Do anyone need more time? Okay, does anyone still need more time? 3, 2, 1. Ooh. Oh, that's interesting. The answer is 3. Because there's a factor for these two things, and there's the utility. There are 3. There's a factor for each conditional probability table, and there's a factor for the utility. There's a factor that specifies for each combination of weather and happy my utility, about how good it is to me. So if the weather is sunny and their happy is true, then maybe it's it's 100. When the weather is rainy and the happy is true, maybe it's 70. Maybe if it's sunny and false, the happy is 20. Maybe rainy and the happy is 0. But it might be, of course, that they're happy if it's rainy and you give them an umbrella, right? But it might be the case that if they're happy if it's sunny and you give them sunscreen, right? Maybe whether they're happy depends on the weather and what you give them, right? Any other questions? Okay. Next question. The initial factor that isn't a conditional probability is a factor on which variables? All right, anyone need more time? 3, 2, 1. What? It's this factor. The initial factor that is a conditional probability is this factor on weather and happy. The answer is D. There isn't a factor for gift. There's no factor for decisions. It's this factor. We just did it. You need this factor, and this factor. Let's go. If I look at this, I'll view. If I look at this factor, there's a factor for this value, which is the probability of an accident given which way you go. There's a probability for you, there's a factor for utility that specifies these other ones. But there's no factor associated with which way or where pads. There's no factor, it's not as though I get to choose. I've got to choose these values for them. Right? So there's a factor for the probability, there's a factors for probabilities and the factor for utility. Just remember that, okay? I'm glad you all got it wrong because that's how you learn things, by trying and doing it wrong. So, okay. Any other questions about that? Yes?
Happy dependent on the weather or the other factors?
No? Wait, sorry. Happy. Wait, let's go back here. I'm lost. Whether you're happy depends on whether and what gift you give. That's right. So you have this happy on gift and weather. You have this factor. You have this factor, probability of weather. You have this happy given gift and weather. Happy given gift and weather. And you have the utility as a function just of weather and happy.
But the question isn't a conditional probability. You're asking which one is not a conditional?
I'm saying which factor is not a conditional probability. So there are three factors. There's this factor that's a conditional probability, there's this factor that's a conditional probability, and this factor, the utility. There's this one.
Yeah, you just said both of them are conditional.
What? Sorry, there's this probability, there's this one, and there's this one. Weather by itself wasn't an option anyway. It's conditional on nothing, but it's still, this one here, that wasn't an option anyway, no one said that, so it's definitely not gift. There's these three, there's this probability, there's this one, and there's the utility. Yeah.
But isn't happy conditional?
Happy is conditional on gift and weather. That's right. There's one factor that isn't a conditional factor, and it's the utility, and it's a factor of which two variables, the factor of weather and happy. There is a factor. The initial factor that isn't a conditional probability is a factor of which variables? There's a unique answer for this. And it's certainly not gift. What if you might think? Yeah. There are probabilities and there are utilities. There's one utility. I have to give it as part of I'm providing it as part of the model. I have to provide this, this, and this. Any other questions? So the three factors I have to provide. This utility factor is a function of weather and happy. And if I'm building this model, I have to provide two factors. This model, I have to provide two factors. I have to provide the table for accident and the table for utility. There are no other factors. There's no factor associated with which way and where pads. All right. All right. So what we're going to do today is we're going to do computation on this. We're going to work out how to find the optimal policy for a single stage decision network, like the one of the questions and the other one, the two we've seen. We're going to model then we're going to look at multiple stage decisions about where we just don't get to make a decision. We get to make decisions based on observations of the world. We get to act and then observe and then act again, and keeping acting and observing. And then we're going to look at how to find optimal policies for those decision networks. All right. So you know what? So now we've got the whole lot of random variables on x1 to xn, and we have the utility that depends on some other variable, some subset of these variables, like we did before. Okay, so if we wait a minute. So if we go in here, oops. So if we look in this one here, we got the expected, you've got the utility here as a function of which way where pad's an accident, and the random variables here is just accident. The utility depends on some other set of variables. the expected value of the utility, given the decision, is we're going to sum over all of the worlds, the x1s, given this d times the utility of the parents of the utility. And the same way we did before is when we have this probability of we're going to sum out all of those variables because that's the expected value. The same thing we did before is we then have this sum over this product, and it's exactly the same as we did before. So it's just now the sum over the product, and the algorithm is essentially the same. So if I have a policy, I can compute the expected value just by summing, and the same algorithm works. I'm just going to use all these three factors, and I can just multiply them together and sum out. Here, I'm going to sum out weather happy. And I can end up with this expected value. So that's what we're going to do. Is we're going to find an optimal decision. I'm going to create a factor for each conditional probability and for the utility. I'm going to sum out all of the random variables. And this is going to create a factor on this decision that gives the expected value for each d. Okay, and we're going to choose the d with the maximum value. So let's look at this. So if I have this network, I have two initial factors. I have the probability of accident given which way, and I have the utility of which way the accident and whether I wear pads. So I have two in here, and now I'm going to multiply them together and sum out now I'm going to sum out, we're going to sum over the accident of this factor 1 of which way and accident times this other factor of which way accident and wear pads. And this is the factor on which variables. I'm multiplying these two together and summing out factor, accident. So what's this a factor on, the result? What's this a factor on, the result? Which way? And what else? We did this lots. Multiplying these two together and summing out accident. What's it a factor on? Sorry? What do you mean the same? You mean it should be which way accident and wear pads? Is that right? Oh, come on, this is what we've been doing. You got that clicker question right. We're summing out our accident. Right, which accident is not, because we're summing it out. Right, and we have this table on which way wear pads, and it has some value. All right, it's either long or true. What's the value for this? oh, we've got to multiply these two together. So we've got to do the case with an accident. So it's 0.01 times what? So this is summing. This is long way true. I've got to sum over the two cases of accident or not. So I've got long true and accident is true. What's that value? What's the value for the first one? 0.01. What's the other one? Long accident and accident. Sorry, I can't read it. What is it? Whether accident is true. Long true, true is what? 30, thank you. Plus, where it's so long with accident is false is 0.99. And what's the case where long where pads is true and accident is false? 75, right. Okay. And if you do that, we're going to end up with this. You end up doing that, you end up with this. If you end up for all the combinations, you end up with this. Here's it's just summing over that. So what should we do? What should the agent do? Gets to choose. So what does it want to do? Right, wants to go the short way and wear pads. Wants to choose the maximum value. It gets to choose. Or it gets to choose which way it goes and wear pads. So it's 83. It's going to choose to do, it's going to choose to, so it will, so the agent will, which wants to maximize its expected utility, will go the short way and wear pads. And wear pads. And the expected utility is 83. Because summing it out, all those other variables just gives us the expected value. Right? It's just the sum of the probabilities and the utilities. Okay, are there any questions about that? So what we're going to do is just the same algorithm we've done before. We're just going to throw in this extra utility. So then we're computing expected value of utility. And we end up with just a function of our actions. And we're just going to choose the best one. It's going to choose the maximum. Okay. Questions? Okay. So what we're going to do now is we're going to look at sequential decisions. So an agent doesn't carry out a multiple-step plan, ignoring information it received between actions. So this assumes we made all of our decisions up front and then the world acts. We don't want to do that. We'd like to observe some of the world and act and assume we're going to observe the world in the future. So we're going to work out what to do when we receive information between actions, we act and receive information. So more typical scenarios, the agent observes, it acts in the world, then it observes more than it acts and keeps going on, right? Here was the model of our agent before. We had observations, acting, observations, and acting. And now, so previously we just did this one here did all of our acting up front, and then the world one, we typically want to observe and act and observe and act. And it's interesting because subsequent actions, what I do subsequently depends on what I observe, because I'm assuming I'm going to observe the world. So what I'm going to do subsequently depends on what I'm going to observe. What's observed depends on previous actions. So what I'm going to do depends on my previous actions, but there's all probabilities involved in here. Another thing that's interesting, so we have this acting, we know future actions depend on my observations. And one of the sole reasons for carrying out an action is to provide information, right? So diagnostic tests are usually bad for you, right? The tests by themselves is usually bad for you. It hurts and has side effects. Spying is bad for countries, right? If you get caught spying, but they each provide valuable information on which to act later. So what we're going to find out is when we do sequential decisions, they end up quite different to this, because we might do things that have an initial are bad, but in the future provide information for us. So part of what we'll look at later is looking at something called the value of information. Okay. So that's what we're going to do. We're going to look at this idea of acting, observing action in sequences. And so what we're going to do is this so-called sequential decision problem is going to have a sequence of decision variables. We're going to make a sequence of actions. And each action is going to have an information set. The parents, so now before we had parent. Now each of these decisions has the information that will be known at the time the decision's made. So we're going to model not only how random variables depend on the previous ones, but what information is available for our decisions in the future. So we're going to have three. So we're going to have three sorts of nodes. So we have three sorts of nodes. We're going to have random variables drawn as ellipses. And arcs into the node represent probabilistic dependence, just like we did before. What does this variable depend on? So it's just what we've seen before, just the same one we had in the belief networks. This is the same node we had in the belief networks. And arcs here, this probabilistically depends on this and is independent of all the other variables given its parents. It's exactly the same definition we've seen. But then we also have decision variables that I get to choose, the agent gets to choose the value for. This is drawn as a rectangle, and arcs into this represent the information that's available when the decision's made. Okay, so arcs into here say, when I'm making this particular decision, here's what information I'll have available to us. And the utility is drawn as a diamond, and the arcs into the node represent the variables the utility depends on. Okay, so there's the three nodes. Here's an example of doing this. So this says that there are two random variables. There's the weather, and there's the forecast. Right, and the forecast probabilistically depends on the weather. But the agent doesn't get to observe the weather. The agent gets to observe the forecast. But whether you're happy or not depends on not the forecast. The forecast is sort of irrelevant. It depends on whether you get the weather and whether you have an umbrella. Okay, so you don't get to observe the weather when you have to decide. But when you do get to observe the forecast, and you've got to work out what to do as a function of the forecast. Okay, so here's this model that says I've got to bring an umbrella. I'm going to see the forecast. The forecast depends on what's happening in the atmosphere. And the weather and my utility doesn't depend on the forecast, but rather depends on whether I get wet or whether the umbrella. Okay, does that make sense? So let's wait a minute. Okay, here's another example. So here's the same fire tampering alarm leaving report. And there's two decisions I get to do. Let's look at this bottom right one. Here I get to call the fire department. Right, and I get to call the fire department, depends on my report. But I also get to this, and I have a first decision, so if there's two decisions. So first of all, I get to choose whether I check for smoke. And I check for smoke. The only information that's available to me is this report, is whether someone told me there's a report. I get to choose whether to check for smoke or not. Whether I see smoke depends on whether there is smoke and whether I check for smoke. And based on this, I have to decide whether to call the fire department. And the information that's available to me when I call the fire department is the report, whether I check for smoke and whether I see smoke. The utility depends on whether there's a fire and whether I call and whether I check for smoke. So there's a cost associated with checking for smoke. And then the utility otherwise depends on just both the fire and whether I check for smoke. Okay? Does that make sense about what we're doing here? So the arcs into this what utility depends on. The arcs into the call are these parents. So if we look at, so in here, if I load this sample problem, this is the fire alarm. Right. So if I look at this one, if I look at view probability and utility, actually, so if I look at the probability and utility, I have exactly the same values that I had before. Why doesn't it let me do that? Right, so if I have this fire, just the same one I had before. So this is exactly the same model we had before, except now we have C smoke is a function of, here I said if there is smoke and I check for smoke, then I see smoke, otherwise I don't. So this is just another random variable we did before. There's no tables associated with check smoke and call, but there's a table associated with utility that here tells me what the utility is, and here we just arbitrarily scaled it between the cost of it. I think if there's a fire and you don't call it, you lose 5,000, and checking for smoke, I think, costs 20 here. Okay, if you do call, so if you don't call and there's a fire, you end up losing lots of 5,000. Otherwise, checking for smoke is reasonably cheap. And if there's no fire and you call, then you lose 200. That's the story. Okay, any questions about that? Yes?
In this case, the utility is 0.
Here, all these models you're trying to maximize. So all I'm trying here, I want to maximize. The ideal situation would be there's a fire, I don't check for smoke, and I don't call, and everything's happy. There's no cost associated with me, nothing happens. The worst outcome here is that there's a fire, I check for smoke, but I didn't call, because I pay the cost of checking for smoke, but then I didn't call, then the house burns down. Right, and everything else is weighed between them. But it's just an arbitrary scale. People do all sorts of things. Okay, does that make sense of what this means? So when I check for smoke, okay. So in summary, there's 3 sorts of nodes. There's the random, the decision, and the utility. There's exactly one utility node. There's only one of these utility nodes. We're not... the random variables and decision nodes have ranges associated, and there's no variable associated corresponding to this utility node, right? There's no utility random variable. There's no utility variable. There's only variables for random and decision variables. There's a factor for each random variable representing the conditional probability of the variable given its parents. So this is the same as we had in the belief network. There's a probability of each variable given its parents. And there's one factor on utility that's the function of the parents of the utility. Okay, so that's the same as we had before. There are no initial factors for the decision nodes. Okay, there are no initial factors for the decision nodes. And, okay, any questions about that? All right. So because we messed that one up, let's do this one. So here's the story. It goes, I've got a disease. So someone has a disease. And from the disease, the symptoms depend on the disease. I get based on the symptoms, I get to decide whether to do a test, or what test to give. Then the test results depend on the disease and the test, but not on the symptoms. Then I have to decide on treatment, but the treatment here depends on I get to observe the symptoms, the test, and the test results. Right? Then the outcome here of this depends on what disease the patient has and what a treatment I give. Right? It's independent of of the test results and the symptoms. Test results and the symptoms, the outcome doesn't depend on that. It just depends on what disease you have and what treatment is given. And then the utility, there's some cost associated with the test, and otherwise it's a function of the outcome. Right? This is the story. So how many factors are there initially, and what are they? So how many factors are there initially? Okay, who can count? How many are there? I heard someone. Five. Any others? Okay, what are they? Yeah. The probability of symptoms and disease, right? That's all. What else is there? That's one of them. Right, the probability of disease. What else? Someone else, what else is there? So I heard outcome. What does it depend on? I can't hear it. My neck hurts too much. I can't see it. You have to tell me. Given treatment of disease. Treatment and disease. And what else is there? Probably a test result. Given test and disease. And someone else, what else is there? There's 1, 2, 3, 4, and you all agreed there was 5 because no one else said anything else. What's the other one? And what's it a function of? Outcome and test, right? Right, there are 5 of them. Everyone happy with that? So when does the agent observe the symptoms? When do you observe the symptoms? Oh. Yes, when you decide to test. Okay, so 5 factors, right? You observe the symptoms before the test. So the agent observes the symptoms before the test. Observes the symptoms before the test. Right, before it has to decide what test to do, you get to observe the symptoms. When does the agent get to observe the test results? So when does the agent get to observe the test results? And? Well, so the agent observes the test results after the test, and what else? Well, no, well, hang on, but Well, you only get to make observations for decisions. So right here, in here, the decision variable, right, represents the information's available to it. It gets of information available for decisions. Okay, so when does it get to observe the test results? Right, so the agent observes the test results before the treatment and after the test. So the agent observes the test results before the treatment and after the test. You can tell it's after the test because it's not a parent of test. Right? We don't have cycles in this thing. We don't sort of get to see things that happen in the future. Does that make sense? Questions? Yes?
Does the symptoms also observe before treatment?
Yes, the symptoms of, yes, the test happens before the treatment. Yeah, so it happens, you observe the symptoms before the test, you do the test, and then you do the treatment. When does the agent observe the disease? So when does the agent observe the disease? So does it observe the disease when it observes the test result? So when does it observe the disease? Doesn't, right? It doesn't observe the disease. The agent never observes the disease. Which is pretty typical in these things, right? You only get to, the only thing it observes, it gets to observe the symptoms and the test results, and then has to make a decision about what to do according to this model. Does that make sense about all these funny arcs mean in here? So this is the information that's available to this agent, so it doesn't get to observe the disease. And the only other question is, does test affect the outcome? So in here. Oh, run out of time. So the answer is that no, the testing here doesn't affect the outcome. Whatever tests you do here, it doesn't affect the outcome. It only affects the treatment. But given I do the same treatment, the outcome is going to be the same. The outcome doesn't depend on the test. We're not modeling an invasive test that might have bad side effects we're only modeling this sort of innocuous test that doesn't affect the outcome. That's what this model says. Okay? So we'll get used to it. We'll play with these models. That's what we're going to play with in the assignment, and this is this model. And they're reasonably straightforward once you understand them. Let's stop there.